Let's look at a common NLP pipeline. It consists of three stages: text processing, feature extraction, and modeling. Each stage transforms text in some way and produces a result that the next stage needs. For example, the goal of text processing is to take raw input text, clean it, normalize it, and convert it into a form that is suitable for feature extraction. Similarly, the next stage needs to extract and produce feature representations that are appropriate for the type of model you're planning to use and the NLP task you're trying to accomplish. When you're building such a pipeline, your workflow may not be perfectly linear. Let's say you spend some time implementing text processing functions, then make some simple feature extractors, and then design a baseline statistical model. But then, maybe you're not happy with the results, so you go back and rethink what features you need, and that in turn can make you change your processing routines. Keep in mind that this is a very simplified view of natural language processing. Your application may require additional steps. Let's take a closer look at text processing. The first question that comes to mind is, why do we need to process text? Why can we not feed it in directly? To understand that, think about where we get this text to begin with. Websites are a common source of textual information. Here's a portion of a sample web page from Wikipedia, and the corresponding HTML markup, which serves as our raw input. For the purpose of natural language processing, you would typically want to get rid of all or most of the HTML tags and retain only plain text. You can also remove or set aside any URLs or other items not relevant to your task. The web is probably the most common and fastest growing source of textual content, but you may also need to consume PDFs, Word documents, or other file formats. Or your raw input may even come from a speech recognition system, or from a book scanned using OCR. Some knowledge of the source medium can help you properly handle the input. In the end, your goal is to extract plain text that is free of any source-specific markers or constructs that are not relevant to your task. Once you have obtained plain text, some further processing may be necessary. For instance, capitalization doesn't usually change the meaning of a word. We can convert all words to the same case so that they are not treated differently. Punctuation marks that we use to indicate pauses, etc., can also be removed. Some common words in a language often help provide structure, but don't add much meaning. For example, a, and, the, of, are, and so on. Sometimes it's best to remove them if that helps reduce the complexity of the procedures you want to apply later. Okay, we now have clean, normalized text. Can we feed this into a statistical or machine learning model? Not quite. Let's see why. Text data is represented on modern computers using an encoding, such as ASCII or Unicode, that maps every character to a number. Computers store and transmit these values as binary, zeros and ones. These numbers also have an implicit ordering. 65 is less than 66, which is less than 67. But does that mean A is less than B and B is less than C? No. In fact, that would be an incorrect assumption to make and might mislead our natural language processing algorithms. Moreover, individual characters don't carry much meaning at all. It is words that we should be concerned with. But computers don't have a standard representation for words. Yes, internally they are just sequences of ASCII or Unicode values, but they don't quite capture the meanings or relationships between words. Compare this with how an image is represented in computer memory. Each pixel value contains the relative intensity of light at that spot in the image. For a color image, we keep one value per primary color, red, green, and blue. These values carry relevant information. Two pixels with similar values are perceptually similar. Therefore, it makes sense to directly use pixel values in a numerical model. Yes, some feature engineering may be necessary, such as edge detection or filtering, but pixels are a good starting point. So the question is, how do we come up with a similar representation for text data that we can use as features for modeling? The answer, again, depends on what kind of model you're using and what task you're trying to accomplish. If you want to use a graph-based model to extract insights, you may want to represent your words as symbolic nodes, with relationships between them like WordNet. For statistical models, however, you need some sort of numerical representation. Even then, you have to think about the end goal. If you're trying to perform a document-level task, such as spam detection or sentiment analysis, you may want to use a per-document representation, such as bag of words or doc2vec. If you want to work with individual words and phrases, such as for text generation or machine translation, you'll need a word-level representation, such as word2vec or glove. There are many ways of representing textual information, and it is only through practice that you can learn what you need for each problem. The final stage in this process is what I like to call modeling. This includes designing a model, usually a statistical or machine learning model, fitting its parameters to training data using an optimization procedure, and then using it to make predictions about unseen data. The nice thing about working with numerical features is that it allows you to utilize pretty much any machine learning model. This includes support vector machines, decision trees, neural networks, or any custom model of your choice. You could even combine multiple models to get better performance. How you utilize the model is up to you. You can deploy it as a web-based application, package it up into a handy mobile app, integrate it with other products, services, and so on. The possibilities are endless.